Now we're going to go to the selection of physical principles and or model variables. For this, we're going to first discuss the general conservation equation. So this equation is a general way of seeing the inflows and outflows of our stock, and these flows are of course dependent on have a time dependency, and can have also internal transformations, which can be seen as generation and utilization or generation and degradation. And these transformations can occur due to biological or chemical processes. So within our model development, we need to select equations, and so we will have basic dynamic equations, and these basic dynamic equations will include mass and energy balance mostly, auxiliary non-dynamical equations, and basic laws. So for instance, if we are talking about change of mass of one component, we may have an energy, we may need equations of that defined if we have, for instance, a change in evaporation, we may need to define how, if it's dependent on the surface area, how the surface area can be calculated, right? And then those are additional equations that we may need. And if we're talking about physical laws, we can talk about, for instance, chemical balances, or we can talk about physical laws like the gas, universal gas law, for example, for defining pressure or defining initial temperatures, etc. So first we're going to start with the mass balance. This is a general equation, and in most of the time we simplify these equations by saying that we are at steady state conditions, which means that we don't have mass accumulated within the system, and that will take off the differential component, right? The change of the mass over time. But in this case, in modeling, we're going to have always dynamic systems that change over time, and then eventually that reaches steady state conditions. So when the mass of a system is not constant, we generally need to know how the mass varies as a function of time. And this is what we want to know. So we have mass in during a certain period of time, and this mass of E is transported into the system. The system is not necessarily a physical region. The system can be something that is defined, that it is a reservoir of our stock, because we can also call reservoir or stock. So we can talk about, if we're talking about nitrogen in our ecological region, if we're dealing with modeling nitrogen or any other type important nutrient, carbon for instance as well, we can say that nitrogen that is accumulated in vegetation, so vegetation is then our system, and then we need to know what are the inflows and outflows of nitrogen in vegetation or nitrogen in soil, for instance. And then we define the flows going in and out. So then we have, as continue with the mass balance, mass out, and we have generation. So, and we have consumption. And this can be, as we mentioned before, if we continue with the example of nitrogen, This can be, then we won't be talking about nitrogen, but we will be talking about one important component of nitrogen. So we can talk about a nitrate, or we can talk about ammonia, and then how this ammonia is being accumulated, is generated. Well, it can be through a chemical reaction or through a biological reaction, for instance. And then we have the component, the accumulation component. So let delta M be the mass of A accumulated in the system during time. It may be either positive or negative. So at the end, this is the type of equations that we're going to have. And depending on the system, we may have flows in or flows out, or we won't have any of these, and we will have only generation or only consumption, right? But as we mentioned before, we most of the time we deal with concentrations. So another common form of steady state mass balance is based on volume, which is like concentrations, right? The reason for this variation is that reaction rates are usually expressed on a per volume basis. For example, the rate of a first order reaction is expressed in terms of the concentration of reactant, where RC is the volumetric rate of consumption of A by reaction, K1. K1 is the first order reaction rate constant, and Ca is the concentration of reactant A. We're gonna have discuss this example on mass balance based on volume. It is a tank with an input stream Fi carrying a dissolved substance A with concentration Ca initial, and that this substance is subject to transformations. So our general expression on the mass balance has to be, if we have values of concentration, then we need to know the values of the volume. And if we have flows, different flows going in and out, that will mean that we also have a change in flow, in volume, and we will also have a change in concentration. So the general expression of the change of mass as a unit of per time can be changed to a change of volume and concentration per time. And then this differential equation can be split into two differential equations, and then that contains the flows in and flows out. This is what is called a stock flow balance equation, where Ra is the reaction rate of the substance A, and the mass Ma has been expressed as the product of concentration and the control volume. So in order to have everything consistent in terms of mass, every value of the flow in and flow out must contain of the concentration in and concentration out must contain the associated flow. So if we multiply the flow, which is in units of volume per time, by the concentration, which is in units of mass per volume, we will end up with the flows in terms of mass, all right? And then for the reaction component, we will have to multiply Ra per volume. So this is the volume in the tank. We may not have the solution or the explicit value for each of the flows. For example, we can have a flow out that is dependent on the friction and on the height, and then we can have we will need to replace this value. We may not have the volume in the tank, but we may have the height and the area. So that means that instead of having a change on volume over time, we may have a change of height multiplied by the area, okay, by the by one of the areas, and then by doing this we can estimate the change in volume. Another simplification that can occur in this type of equations is that if the flows in and out remain the same, which means that the height or volume of the tank remains constant, we will only have a change in concentration. And we can simplify by having only one flow, multiply by the initial concentration minus the concentration that is occurring per time, and then plus minus the reaction, right?